So the real reason we developed z-scores is so that we could use the 68, 95, 97.5 rule and actually really a normal distribution. So what is that? There's a distribution we keep seeing when we work with statistics, and let's take a look at flipping coins. So first of all, if I flip the coin once, I expect to get heads maybe 50% of the time and tails 50% of the time. And you can say one of those is 0 and one of those is 1. If I increase this by 1 to 2 coin flips, then you find out that I would get 0 a quarter of the time, 1 head half the time, and 2 heads a quarter of the time. If I move it up to 3, then you see that it's starting to break up a little bit more. And if I have 4, there it is. And as I add more and more coin flips, you notice the distribution of heads starts to take a shape. And this is a very popular shape in statistics. This is approximating a normal distribution. And here you can see a little bit more of a close-up. So don't worry if it looks skinnier in one aspect or wider in another. That just has to do with the scaling of the image. So we've studied this normal distribution and we found that approximately 68% of the data is within one standard deviation of the mean. 95% of the data is within 2 standard deviations, and 99.7% of the data is within 3 standard deviations. So you can probably see where the name for the rule comes from, the 68, 95, 99.7 rule. So how could we use this? Well, let's take a look at a study in 1903 on inheritance where we were calculating the heights of mothers. And the average value for the height was 62.484 inches, and the standard deviation was 2.390 inches. According to the empirical rule, what is the interval of heights for 68% of the population? Well, 68% is just one standard deviation from the mean on both sides. So we just need to add the mean to the lower, subtract the mean from the mean minus 1 standard deviation to get the lower value, and add 1 standard deviation to the mean to get the upper value. So the range of heights for 68% of the population is 60.094 to 64.874 inches. Now I'm going to put a little twist on it and ask you what percentage of the heights are less than 67.264 inches. Well, I still need to go get the z-score. The z-score is going to be this value, 67.24, minus the mean divided by the standard deviation. And I get a z-score of 2. So what does that mean? Well, you might be tempted to say the answer is 95%. But 95% is 2 standard deviations away from the mean on each side. There's actually some more data off here on the left, and I said less than 67.24. Luckily, we know that half of the data is below the mean and half of the data is above. So what I'm going to do is say this half of the data is just 50% because I'm counting everything. And I'm adding this half of the curve, half of 95. And I get that 97.5% of the heights are less than 67.264 inches. So why don't you go ahead and use the 68, 95, 99.7 rule. So we have a study investigating the effect of car speed on accident severity. And the vehicle speed at impact was recorded for 5,000 fatal accidents. The mean speed was 42 miles per hour, and the standard deviation was 15 miles per hour. What was the range of vehicle speeds for 68% of the data centered about the mean? Go ahead and just add 1 standard deviation to both sides of your mean. For 95%, you would add 2, and for 99.7%, you would add 3 standard deviations. By the way, try to figure out why I have 0 here. So when can we use the 6895-99.7 rule? Well, if the shape of the data is unimodal and symmetric, you can. Please, please draw a picture, draw a picture, draw a picture. If you try to use this and inappropriately and you don't draw a picture, you will not get credit for it. Okay, also, so never use the normal model without checking that this applies. Now, if you want to go ahead and do the calculator, and it will actually look up data for not just one standard deviation or two or three, but other numbers as well. And the cool thing is you can put lower and upper value numbers. So you could say 3 standard deviations below to 2 standard deviations above. So how does it work? First of all, you're going to press second and distribution, which is right at the vars. Then make sure you pick number 2, which is normal CDF. Then enter your lower z-score and a comma and your upper z-score. So here I'm just doing 1 standard deviation away, and you can see there's a 68%. I can also do this for 2 standard deviations away from the mean, and I should get the 95%, which it is, about 95.4. And finally, do 3 standard deviations away from the mean, and we should get our 99.7%. So you can use this anytime you need to calculate the probabilities or the percentages between 2 different z-scores.